older videos you do are like halfway through the lesson. They're gonna
Halfway
be like,
into the
what was
lesson.
the first part of this?
So I'll just have to repeat it again for those who are sleeping. So we can use a tangent line to approximate any curve really close to the point of tangency. So it's like taking a curve like y equals sine x. I can approximate sine of negative 0.2 with the line y equals x because negative 0.2 is close enough to 0 that y equals x is a good approximation. As a matter of fact, sine of x, you can go quite a ways out. If you look at our graph here, I mean, how far out? When I look at my graph right here, I can trace quite a ways out. I mean, relatively speaking. Look at this. I can go, this thing looks like a line to me through this whole screen shot. And look at where I am. I'm at negative 0.625. That's a pretty big interval to be able to use a line to estimate the curve. I can go from negative 0.625 all the way to 0.625. That's pretty big. Okay. Like with an exponential function, I can't really do that. Exponential function, you're going to notice that the tangent line gets far away from this pretty quickly. Like if I were to draw a picture here of an exponential. So here's an exponential going like this. If this is my tangent line right here, I better not use my tangent line anywhere outside of about right there as an approximation for my exponential. But my sine curve, man, that's a pretty big range. From negative 0.625 to 6.625, that's like 1 point, more than 1 in terms of the range there. So that's pretty good. But it varies from function to function. And then with differentials, so going back to the differentials here, now that we're recording, we can use differentials to estimate like a rate of change. Okay, so differentials can be used, and a differential just involves a derivative. And we're going to take the derivative of the volume formula. Does anybody know the surface area formula? You almost quoted it. You guys kind of had a mixture of the volume. For a sphere, do you remember what it is? Yeah. What is it? It's the 4. Yeah. So here's where it comes from. If you take volume, so take volume equals 4/3 pi r cubed. Okay, use the power rule on this and you drop down to surface area. You guys with me here? So use the power rule on this and you get surface area equals 4 pi r squared. So this 4 pi r squared is what we would call the differential. It's the derivative of the volume function. So the differential measures the rate of change for a given r. You give me the r. This surface area question will measure the rate of change, okay, for that given r. The rate of change of the volume, actually, because this is the derivative of volume. So it says use differentials to estimate the air in the surface area of the Earth if the radius is measured as 3,959 miles plus or minus 0.1 miles. So what we do is we just plug in here to the differential, or the derivative. I'll just call it the derivative. Let's call it dv dr, which is actually what I labeled s. Okay, so dv dr, we have dv dr equals 4 pi r squared. And we just do a little bit of algebra here. The differential is the dr here, so we've got dv equals 4 pi r squared dr. And dr, we treat dr like an independent variable. You're going to plug something into that. And when you solve this, dv equals 4 pi r squared dr, where dr represents, remember, dr is delta r. What does delta represent? Change. What's the change I'm suggesting here? It's a plus or minus thing, which is 0.1. What's the radius that was initially measured? 3,900. So we're going to go like this. We've got dv, which is the differential here, is equal to 4 pi 3959 squared times 0.1. Go ahead and calculate that. And this says, it speaks to the amount of change that could happen if you were just off by 0.1 miles? Like, how different could you end up with in terms of the surface area? It's like 9,000 something.
Like
19. Oh, in terms of the, oh, I see. Okay, for surface area, yeah. I probably didn't take it to the. Okay. So that's what that is an estimate. That's an estimate of the surface area. So what'd you get? Was it 19 million? Okay. So let's see what the difference is here. We want to see the difference. How did you figure out the actual? So this is what it is with just that 0.1 difference. The actual would be just 4 pi r squared. What do you get with 4 pi r squared? Have it in here too.
It's
So what's the difference between those two? Okay, quite a bit. So just being off by a little bit. But let's do this. I actually goofed on this. I'm at the wrong level here. I didn't read that carefully enough. So this would actually be the differential for the change in volume. You with me? So you said it was like a 19. How much it would change the volume? 19 million. Okay. The change in surface area is not quite that dramatic. So that the differential for the change in surface area would mean taking the next derivative. So dv dr equals 4 pi r squared. What would the next derivative be here if we took, so ds dr, what's ds dr here? So this dv represents the change in volume. I actually want the change in surface area. So I've got to go one level down from surface area. It takes it, and that's the differential for surface area. So ds dr equals 8 pi r, right? So ds would equal 8 pi r times 0.1. This won't be quite as dramatic, but it's still pretty dramatic. So what's the difference? So it says, what is the air? Use differentials to estimate the air in the surface area, not the volume, sorry, of the Earth if the radius is measured as 3,959 miles plus or minus 0.1 miles. So I plug in here 8 pi 3959 and then times 0.1. And what do you get with that? This is the 9,000 number I was thinking. Okay, 9,957. So that's the ds. So that's the potential air, which is pretty big. The air was astronomical for volume. So yeah, because you're cubing it, but the air for volume was huge. Yeah.
So the volume one should be 4 pi r cubed.
The volume equation is 4/3 pi r cubed. Yeah. And then you take the derivative of that to get the estimated change in the volume, not the surface area. And then you got to take the derivative of surface area to get the estimated change if you were to be off by 0.1 mile in the surface area. So this is the change in surface area. I did the volume first. Sorry. Yeah. Yeah. And then it's okay. And then okay, it doesn't quite work out right here. 8 pi r. So what does 8 pi r look kind of like? It kind of looks like it's kind of close to 2 pi r. It's actually 4 of the 2 pi r. What is 2 pi r? Circumference, right? So 8 pi r is actually has to do with something like a great circle. If you go back to geometry, I'd have to look back at it, but it has to do with the great circle. But it essentially goes 3-dimensional is volume, 4/3 pi r cubed. Take the derivative of that, you get the surface area. Take the derivative of that, you get sort of circumference, but it's like having to do with the great circle, not like circumference of a 2-dimensional circle, obviously. So, but that's the relationship. But differentials, what differentials do is they will estimate the rate of change. It's not hard to find actual, like another example they give in the textbook, they give one about like the circumference of a tree growing. So you can use the derivatives to estimate, you know, the rate of change of the surface area of the stump. And then you can do the actual. What is the actual if it goes from, say, a radius of 10 centimeters to 10.1, you get the actual. But with differentials, just taking a derivative, you can get a pretty good estimate just plugging in the original 10 and then the change 0.1, and it'll be pretty close. And so that's the idea with differentials. So differentials are a way of estimating change, whereas linear approximations are a way of estimating the y value or output of a function very close to the point of changes. So there's the connection. That's why they're in the same section together. So let's go back up here. So quick review of tangent lines here. So if you have a point xy and a slope m, what's the equation of the tangent line? Can you do it in point slope form? The question is, if we have a point at xy and a slope of m, what is the equation of the tangent line in point slope form? They overcomplicate this in the book. I'm going to simplify. We're going to make this algebra line with a little bit of calculus to find out. So, yeah, I want point slope form. What is point slope form? Okay, and then if you really feel the urge, you can go ahead and change this up to slope intercept if you want. Or what they'll oftentimes do is just write it like this. This is how it's written oftentimes in the key. So there's the equation of the tangent line. We've already done this a little bit. Find the equation of the tangent line. So in the textbook, they call this linearization. They use this function L, and they do it in terms of f prime of a and all this stuff. But really, a linearization is finding the equation of the tangent line at the point, and then using that function to estimate a particular x value that they give you to plug in. That's all you're going to be doing. It's super easy. So that's your tangent line. So the only two pieces you need are m, right? So you need m, and you need a point. That's all you need. How do we get m when it comes to calculus? Let's think about what it would look like to write the equation for the line tangent to the graph of y equals square root of x when x equals 64. Let me draw a picture for you here. I'll let you write this down. So y equals square root of x looks like this. Way out at x equals 64, my tangent line is going to be almost a horizontal line. So write an equation for the line tangent to the graph of y equals square root of x when x equals 64. So we're going to use point slope. We'll just put it in point slope form. You can just do that. You might have to solve it for y so that you can estimate it. And then I'll have to show you the notation in the textbook. You should look at the textbook for notation, but they really overcomplicate this. So the equation for the line tangent to the graph of y equals square root of x, this is what we're going to call the linearization. This is the linearization of square root of x at 64. So it's this. We've got y minus y1 equals m, x minus x1. Let's put some calculus into this. What does m actually equal to? Slope. Okay, but in terms of calculus, it's the derivative where? Yeah, so this is f prime of 64. And what is x1? Yeah. I liked his notes better, so I'm using this formatting. But yeah, so we've got x minus 64, and then I need y1, so I got to find y1. How do we find y1? Plug it in. So where do we plug it in right here, right? y1 equals square root of 64, which is 8. We just found the linearization. Well, so we got to do a little bit of calculus. Yeah, we got to find the 64. But this is the linearization. So what is first of all? Y prime is equal to what? 1/2 x to the negative 1/2. Good. So that means f prime of 64, y prime is equal to f prime of 64 is 1/2 64 to the negative 1/2 power. So we take the derivative of square root of x, and then we plug in 64, and that'll give us the slope of our linearization. Remember, linearization is the same as the equation of the tangent line. So this is nothing new. We're just calling it something different. So what does this look like here? So we've got 1 over 2 times the square root of 64. 1 over 2 times 8 is 1/16. So y minus 8 equals 1/16 x minus 64. Box your answer. You just did some algebra 1 with a little bit of calculus. Okay. So we found, right? So, and then they might ask you to plug in a value and use this to estimate it. But 1/16 slope is pretty close to horizontal. Pretty darn close, which makes sense looking at the picture. You'd have a very different tangent line or linearization as you get closer to x equals 0 for this curve. But way out at 64, that's it. So box that. We good with? Are we okay on that example? So I'm going to give you different functions and ask you to find the linearization. That's what you're doing. And then I'm going to ask you to estimate by plugging in the value. So if we wanted to, we could estimate maybe what would the x value be at 65 or at 63. Or we could just plug it into the original. But this is using linearization to estimate it. All right. Last little slide here, and then we're going to go back to that exploration on extrema. Okay, can you guys write the equation for the tangent line to the graph of y equals cube root of x when x equals 125? Do you know what cube root of x looks like? Might want to graph it and look at it. Might want to graph it and look at it.
It's one of those.
It is a squiggle, but we looked at lots of different squiggles. What does it do? What's its end behavior model look like as it goes all the way up to x equals 1? Okay, so go ahead and see if you can find the equation of the line tangent to the graph of y equals cube root of x when x equals 125, or this is called finding the linearization. I'd like you to try that. A little bit of fill in the blanks here. We've got y minus 5. You plug 125 in there equals something x minus 125. And then we've got Zach, did you get that derivative? No. Fun with fractions. This is something that'll be like one part of the response. I'll ask you to find the linearization. They will call it probably the linearization. They might call it the tangent line. They might also throw in, just as an extra part, find the normal line while you're at it. Do you guys remember what to do to find the normal line?
Sure.
We can talk about that once we get M here. All right, what do you guys get for y prime and 125?
Plus 5? Oh, no. 110.
You get what? 1 over 75. So that's the tangent line. So you should think about how would the normal line. What would be different about the normal line? What would be actually it would be negative 75. Don't confuse it with that theorem about f inverse prime, which is just the reciprocal and that's opposite. But this is opposite reciprocal, just like you learned, for perpendicular lines. That's what normal means. Okay, so that's it. Let's do another one here. Let's go back to. Well, before we go back to. Okay, can you use, guys? Can you use this tangent line to approximate the cubed root of 122? How would you approximate the cubed root of 122? This is not putting in your calculator, doing a decimal approximation. How would you use your tangent line or your linearization? Okay, once again, cubed root of x is not a line, it's a curve. It's a squiggly thing. Okay, so it's curved. So we found a line to estimate the squiggly thing really close to 125. Is 122 fairly close to 125? For this function, yes. Just like for that square root function, you could go quite a ways away from 64 on that, and still the line would have been a pretty good estimate. Like your error between the actual curve and the line would not be much, because square root of x absolutely levels out as you get farther and farther to the right. So what about here? Where am I plugging in the 122 here? Yep, plugging it in for x, you got y equals 1 over 75, 122 minus 125, plus 5. Don't forget the plus 5 over there. And what do we get as an approximation here? And then we're going to plug it into our calculator to see how close we are. So 1/75 of negative 3 plus 5. What do you guys get? The decimal approximate or a fraction. What do you have? Just as a decimal would be fine. 4.5. Okay. What's the actual of cubed root of? So this is our approximation using the line. 4.959. Okay, so pretty close. Pretty good. That's because of the end behavior model of this. As x gets really big, it's going to be pretty close. With the exponential function that I drew you, the linear approximation, you better stay a little closer. Well, you're okay when you're close to the to 0, 1 with it, but as you get farther away to the right, it's more problematic. Because I guess if you go to the left, it's a little better. You can have a bigger interval. What's that?
Go to the right part.
Yeah, that's true. I don't know, but right where I drew it in that curve, I mean, your tangent line gets far away from the curve pretty quickly. All right. Let's go back to this guy again here. Now we use the line y equals x. Was y equals x the best line to use for this guy? Okay. How would you get a tangent line approximation for that sine x that I started with? At negative 0.2. So we've got y minus something equals mx plus 0.2. So that's what I have. So we have the function y equals sine of x. What's the derivative of that? I got y prime equals cosine of x. So y prime of negative 0.2, whatever that gives us. What's cosine of negative 0.2? That would be your slope right here. Very close. So we have 1 in here. And then we have y minus, if we plug in to the original, sine of negative 0.2 is, I don't remember what it was. Sine of negative 0.2. We're really close to, yeah. So we have y, 0.2. So when all is said and done, when I solve this equation, guess what I do? So that tangent line that we decided in the very beginning as a linearization of sine close to 0 of y equals x was the actual linearization. So any questions on that? Linearization. They're going to ask you to do some differentials. Okay, guys, all they're asking you to do is define the derivative, move the bottom part over. That's the change. And you'll see in there they will propose a change from the original. You plug it in, and that's your differential. That's your estimate. Which may not be perfect, just like the linearization isn't perfect. But really close to the point of tangency is a pretty good estimate. Do you have any ideas of where they might use this in real life?
Not possible.
Linearization. It's essentially linear. What's that? Racetrack? Racetrack? Yeah, in terms of the rate of change. The rate of change.
You said race? Like racetrack? Yeah. No. What? That's not start. Oh, what? What?